Part of our unit in stoichiometric relationships is on gases and how they behave. And it's very, very handy if we can actually understand some of this before any test or exam on the topic. We are basically looking at the idea of the kinetic theory. And as you know, the kinetic theory tells us that the particles are randomly moving, but they keep moving all of the time. The only time they would not move is when they get to that hypothetical situation called absolute zero, and in that case it means there is no motion. Now, with the kinetic theory, as with all, it's a construct we make to help us understand how things happen. And it's very interesting to think about there are no attractions between particles, which goes against everything we'd think about in terms of opposites, charges having an effect on each other, or the same charges having an effect on each other. And since all matter is basically a mixture of positive and negative charges, it makes it rather unrealistic, but it does give us a good indication of what's going on. Right, so let's think about what goes on in terms of atoms and molecules in a gas. Most idea of the trouble we have with gases and other things is we don't realise what actually is going on. And it's hard to imagine it because it's something occurring at the micro level. It's occurring at the atom level or molecule level. So if we imagine that we have these blue gaseous atoms, right? We could talk about a property of gases called pressure, and pressure is how much push they are doing against something. Now, typically refer to pressure as a container, but it can be pressure against us, it can be pressure against anything. But if we think about it, it's all due to the atoms hitting the container or the atoms hitting us. And that changes. If we squash the atoms together, obviously we're going to have, as in the case of the second diagram, if we push all the atoms together, then we're going to have actually more atoms there. So obviously there is going to be a bigger push against us. And it's very interesting that we think about this because not very often do we encounter single gases that exist together, right? We basically live in a mixture of gases. The air, as we know, has mainly nitrogen, a little bit of oxygen, and some carbon dioxide and various other gases. But the whole pressure of the air we normally talk about as 1 atmosphere, or enough to raise a mercury by 76 centimetres, or if you like, in the new terms, around about 100 kilopascals of pressure. But all that pressure is to do with all of the atoms in there, and each of the atoms inside, or each of the gases inside, exerts its own pressure, and that will of course be based upon how much of the gas there is. And this is basically Newton's law of partial pressures. Now, diffusion is a property of gases that is easy to explain. We know that in gases the particles are spread out and they're moving. So that means there seems to be a heck of a lot of empty space. That means that other things can take up position in that empty space. So if I get some ammonia at the front and then open the bottle up and gently heat it, the smell of ammonia soon spreads all the way through the room. And that's because the ammonia gas particles are able to move between the air particles and spread out. And this is basically the way diffusion works. As we can see down the bottom, I start off with all of my red particles all in one spot, and as soon as I take off my imaginary lid of my ammonia, it spreads out and occupies all of the space. That's one thing about gases, they spread out to occupy as much space as they can. So if I'm in a room, they will spread out to occupy all parts of the room. We know this because we don't suddenly run out of air in one part of the room compared to another part of the room. Now the other thing that space allows us to do is to compress the gases. If you've got space between things, you can squash them and move them closer together. But normally when that happens, they will try to move apart again. there'll be a fair bit of repulsion going on, and they'll be trying to move apart. And if you think about what it's like to try to compress air using something like a bike pump, you know that it gets harder and harder and harder as you put more and more gas particles together, or as you compress them more. The final thing that I want to talk about in this video is about temperature. Now, temperature is not really how hot or cold it is. It is based on the average kinetic energy of the particles. So in the case of our first one, if we look at this graph here, it's a nice little description about what goes on in terms of gases. The red graph corresponds to what goes on at minus 100 degrees C. Now we see that we have the average particles peak at the top of the red. Alright? And it tells us my average speed is somewhere around about 300 metres per second. And that's okay. But we've got a few above and a few below. So our temperature is based upon the average side. But if I heat the gas to 20 degrees C, I get the green curve. Now notice that the green curve is lower, but also notice that it's more spread out. So the same number of particles are shown in both graphs. It is just I've made the average kinetic energy higher, and it means that some atoms have much, much higher energy, while some atoms still have low amounts of energy. And the third one shows us what actually happens if we increase to, say, 600 degrees C. Again, we see we have the average speed, noted by the top of the curve, is around about 650 to 700. Right, so the particles have got faster, more particles are faster, and some particles even have a speed greater than 1400 metres per second. Now this we use a lot, this curve, and we use it to explain things a bit later on in terms of our energy topic, so keep an eye out for it there. But hopefully you now see that the temperature is all about the speed of the particles.